Now see the theorem here. It says that a language L over the alphabet sigma is regular if and only if there is a finite automata with input alphabet sigma that accepts the language L. We all know the acceptance definition of acceptance of any language by an automata. Meaning of this theorem is if M is any finite automata, there is a regular expression corresponding to that language. Remember that if the finite automata is there, its regular expression has to be there. Similarly, the next statement says that given a regular expression, there is a finite automata that accepts the corresponding language. Means if we have a regular expression, we must have a finite automata. The finite automata is accepting that particular regular expression. Means there is a finite automata that accepts the corresponding language. So the theorem is hopefully clear to all of you. Let's see the next concept. Now we have extended transition function, that is delta star, for non-deterministic finite automata. Recursive definition for this non-deterministic finite automata. Let M is Q, sigma, Q naught, E and delta be any non-deterministic finite automata. The function delta star is Q cross sigma star to power set of Q. It is defined recursively as follows. For any small q that belongs to the set of states, delta star q comma null is q only, that is subset q. For any q that belongs to q, y that belongs to sigma star, that is y is any string that is coming from sigma star, a is any symbol that belongs to sigma. Delta star q comma ya is equal to union of what? Any element r that belongs to delta star q comma y, and this r transition function of r comma a. Now we will find the output of any extended transition function by taking some example. We will see both the cases, that is the base case and recursive case in this definition by the given example. Assume this is a non-deterministic finite automata given in the example. See, q naught on reading 0 is going on q naught. Q naught on reading 1 is going on q naught as well as q1. Similarly, q1 on reading 0 is going on q2. On reading 1 also it is going on q2. Q2 on reading 0 and 1, in both the cases it is going on state q3. Q3 on reading 0 or 1 doesn't have any move, so therefore phi and phi. Assume that we have to find the extended transition function for the given string 11. So it is equal to q naught on the 11. We'll write this as r delta star q naught comma 1 delta r comma 1. So that we need to find out this now. Delta star q naught comma 1 is equivalent to delta star q naught null 1. So it can be written as union of r that belongs to delta star q naught comma null delta r comma 1. We know this is the base case. It will return us r that belongs to q naught only, delta r comma 1. Replace this r by q naught, so I'll get this delta q naught comma 1. Now see the diagram. Q naught on reading 1 it is going to state q naught as well as q1, so I am getting the subset q naught q1. Q naught q1. So I'll replace this value by q naught q1. So this is the union of r that belongs to q naught comma q1 delta r comma 1. So now replace this value of r by q naught and q1. So I'll write this delta q naught comma 1 union delta Q1 comma 1. So Q0 on reading 1, we know that it was Q0 Q1 union Q1 on reading 1 is Q2. See this diagram. Q0 on reading 1 is Q0 Q1 and Q1 on reading 1 is Q2. So perform the union operation. It is Q0 Q1 Q2. This is the output of delta star Q0 and double 1. The string was double 1. Now suppose for the same example we take another string. If I take this as delta star Q0 0 1, delta star Q0 0 1, it can be written as R that belongs to delta star Q0 comma 0 delta R comma 1. So we need to find out this delta star Q0 0. I will find out this here. Delta star Q0 0 can be written as null 0, which is equal to union of R that belongs to delta star Q0 comma null, here delta R comma 0. We know that this delta star Q0 comma null will return Q0 only. According to the definition, this is Q0. Replace this R here with Q0. So I'll get delta Q0 comma 0. Q0 on reading 0 in the diagram. I'll take you back to the diagram. Q0 on reading 0, it's going on Q0 only. So I get this Q0 here. What I will do, I will write this union R. This is replaced by Q0 delta R comma 1. Now put this R, replace this R by this element of this set Q0. So I'll have delta Q0 comma 1. Q0 on reading 1, it is going to what state? Q0 on reading 1. Q0 on reading 1 is going to state Q0 as well as Q1. So I'll get this Q0 as well as Q1. So this is the output of the extended transition function for the NFA when we are giving the string 0, 1. Suppose take one more example. If suppose delta is Q0 and this time I have taken triple 1, we have already done this delta star for double 1. This time I am taking triple 1. It can be written as R that belongs to delta star Q0 double 1 delta R comma 1. We know the output of this. We found this earlier. This was the output. It was Q0, Q1, Q2. Delta star Q0 double 1, we got the output Q0, Q1 and Q2. We will make use of this output here. So this becomes R that belongs to Q0, Q1, Q2. delta r comma 1. Now replace the value of r by these values q0, q1 and q2. Perform the union, that is delta q0 1 union delta q1 1 union delta q2 1. Perform the union of all these. We will get, by seeing the diagram, q0 on reading 1, q0 on reading 1 is going on q1, q1, q0 and q1. That is q0 and q1. q1 on reading 1, q1 on reading 1 is going to q2. This will give you the union, perform the union q2. q2 on reading 1, q2 on reading 1 is going to q3. So this becomes the state q1 not q1, q2 and q3. This is the output of the extended transition function for the string 111. Now see what we have the idea whenever we perform the intersection of this with the accepting state. What are the accepting state sets here? We have, for this diagram, we have only one state as an accepting state, I think. Yeah, q3 is the accepting state. q3 is the accepting state. q3 is the accepting state. Perform the intersection of this with accepting state. If it is not equal to 5, if it is not equal to 5, then we'll say that this particular string is accepted by the machine. This is the actually definition of acceptance by non-deterministic finite automata. Whatever the output we get through the extended transition function, we perform the intersection of that output with the accepting state. If we get some set or non-empty element, we say that this string was accepted by the machine. Now take this case where we had 0, 1. See the string 0, 1. This one. Perform the intersection with the accepting state. Intersection with the accepting state. In this case, I'll get 5. So it means 0, 1 is the string which is not accepted by the machine. 0, 1 is not the string accepted by the machine. Now what is acceptance by a non-deterministic finite automata? We have already discussed this through the example. See the definition. It says that if M is any non-deterministic finite automata, X is any string, it is said to be accepted by M if we have extended transition function starting from Q0, comma X, intersection accepting state A, it should not be equal to 5. If such thing happen, then only we'll say that X is accepted by the machine. The language accepted or recognized by M is the set LM. LM is all strings accepted by M. So I hope this acceptance by non-deterministic finite automata is clear to all of you. Thank you for watching the video. Please do write your comments.